This is a video for AQA Further Pure Mathematics. This is Sequences and Series, section 2.3, where we're using induction to prove results about divisibility. Well, firstly, I'd like you just to pause the video and consider for a few minutes what it means for something to be divisible by a particular number, in this case 3, and then see if you can prove for these two expressions that they are indeed divisible by 3 for all integers m. Right, well, let's have a look at these then. The first one, we can multiply out the brackets, and of course we get 3m squared minus 9m minus 2m plus 6 and then minus m. And if we calculate what we've got in total there, that's 3m squared and a total of minus 12m plus 6. And we can factor from that 3 to give us 3 times m squared minus 4m plus 2. And this is exactly what we mean by something being divisible by 3, that 3 is a factor of the expression. So we've proved it for the first one. The second one, in a similar sort of way, the first part of the expression, 9 to the power m plus 1, can be written as 9 multiplied by 9 to the power m. So we've got 9 multiplied by 9 to the power m minus 3. And of course, again, we've got there a factor of 3, which we can take out from that. So that's equal to 3 times, and then inside the bracket, 3 multiplied by 9 to the power m minus 1. And again, we've got a factor of 3. So therefore, these are divisible by 3 for positive integers m. Now in the next example, it's not quite so clear where we might get our factor of 8 from. But that's what we'd need to do to show that this is divisible by 8 for all possible values of n, that are positive integers in this case. So it's not obvious where it's coming from, but proof by induction can be used in such cases as this. So a reminder first of all what we mean by proof by induction. We've got these 3 steps to follow each time. Firstly, we need to check that the statement is true for the first case, usually n equal to 1. And then, given or assuming that the statement is true for a value n equal to k, we show that that means that it would also be true for the next one, n equals k plus 1. Then the conclusion is to put those two things together and say that therefore it's true for all integers greater than or equal to 1. So let's look at the first part of this example. In this case, we've got to show that when n equals 1, it's divisible by 8. Well, n equal to 1, we simply substitute the value 1, so that's 2 multiplied by 1 minus 1, and then plus 3 to the power 2 multiplied by 1. So that's equal to 7 plus 3 squared, which is 7 plus 9, so that's equal to 16. And 16, of course, we can write as being 8 multiplied by 2, so therefore it is true for n equal to 1. Well, the second step in the proof is to start off by assuming that the statement is true for n equal to k. Now we've already seen that when we're talking about something being divisible by a number, it just means that that number is a factor. And putting that the other way around, that means that we can write the expression as being equal to 8 multiplied by something. So we normally use a letter, for example, p. So we're saying here that let's assume that 7 to the power 2k minus 1 plus 3 to the power 2k is equal to 8 multiplied by p. In other words, 8 is a factor of the expression. And now what we need to do is to consider what happens when n is equal to k plus 1. Well, substituting our value of k plus 1, then clearly we get 7 to the power of 2k plus 1 minus 1 plus 3 to the power of 2k plus 1. And what we need to do is to show that that is divisible by 8. However, it's again not entirely clear where that's going to come from, so we need to do some work with the expression that we've got, 7 to the power 2k plus 1 minus 1 plus 3 to the power 2k plus 1. Well, the first thing to note is that this is equal to 7 to the 2k plus 1 in total, and the second one is 3 to the power 2k plus 2. Now we need to get 7 to the power 2k minus 1 plus 3 to the power 2k. So just let me just emphasize that what we're trying to do is to get this expression here out of the one that we've got written down. Well, the first part of the expression, 7 to the 2k plus 1, is equal to 7 squared multiplied by 7 to the power 2k minus 1. And the second part of the expression is equal to 3 squared multiplied by 3 to the power 2k. Or in other words, we've got 49 multiplied by 7 to the power 2k minus 1. So 49 times what we need for the first part of the expression, and 9 times what we need for the second part of the expression. Now, as a little trick, we can write that 9 times as being 49 times minus 40 times. So we can write this as being 49 multiplied by 7 to the power 2k minus 1 plus 3 to the power 2k, as long as we subtract from that 40 times 3 to the power 2k. Now hopefully you can see where we're going. The expression in the bracket there is the thing that we are assuming is equal to 8p. So this is equal to 49 multiplied by 8p. And of course 40 we can write as 8 multiplied by 5. So we get 8 multiplied by 5 multiplied by 3 to the power 2k. So that means that we can factor out a value of 8. So it's equal to 8 times 49p and then minus 5 3 to the power 2k. So therefore we've shown that our expression is a factor of has a factor of 8, assuming that the expression when n equals to k has got a factor of 8. So what we've done is said that if it's true for n equal to k, we've shown it's true for n equal to k plus 1. We'd already shown it was true for n equal to 1, so we can put those two statements together and say therefore it's true for all integers n greater than or equal to 1. Well, that's the end of this video on induction, looking at divisibility. In the next one we'll look at induction, this time to prove results about series.